This is lesson 4. We're talking about the complex plane and De-Moivre's theorem. This lesson will show how to represent complex numbers in polar form, sometimes called trig form. First, we have to learn how to represent complex numbers graphically, and that a complex number can be written in the form z equals a plus bi. The a part is the real number part, and the bi is the imaginary part. We'll use the complex plane with two axes in order to graph complex numbers, but the x-axis will now be our real axis, and the vertical axis, the y-axis, will be the imaginary axis. So they'll behave just like an ordered pair on a rectangular grid. So if we want to graph the complex number 3 plus 4i, 3 is the real part and 4i is on the imaginary axis. So starting from the origin, we would go 3 units on the real axis and 4 units on the imaginary axis, and that would be our complex number point A. Point B, 0 plus 2i, is located right here. Point C is negative 2 plus 3i. It's over here. D is sitting on the real axis. It's just that point at negative 4. F is negative 1 on real and negative 2 on the imaginary axis. And then G is over here in quadrant 4 at 3 and negative 1i. Example 2. We're talking about the modulus, or the absolute value of a complex number. So let's say we have a segment OP that goes from the origin out to some point P that has a magnitude, which is a length, and it also has a direction. So if I want the modulus, which is the absolute value, I can find that by figuring out the length of the hypotenuse. So it's not very new information, it's just new symbols. So if we had A on the real axis and B on the imaginary axis, then the modulus or magnitude or the absolute value of the complex number Z is going to be found by calculating that hypotenuse. So we have magnitude, which is length or distance, and we have the hypotenuse, and absolute value. Those are all interchangeable. Magnitude, hypotenuse, modulus, all those words are related to that segment from the origin out to our point P. And we can find the angle, and we can find by using tangent inverse, and we can find the magnitude or the length by calculating the hypotenuse. So one other thing you have to consider is, let's say we were over here in quadrant 2, and you had some segment over there at some A plus BI point. So if this was our angle theta, and you used your calculator to calculate the inverse tangent, and you were in quadrant 2, your calculator is going to give you an answer down here in quadrant 4, because your calculator is restricted to the domain of tangent inverse. So you might want to make a note about that. You have restricted domain from negative pi over 2 to pi over 2. Whenever we're using our calculator and you are looking for an angle that's located in quadrant 2, your calculator is going to give you a quadrant 1 answer or a quadrant 4 answer. In this case, quadrant 2, they're going to give you a negative angle. So if you get this answer, you've got to consider how do I get myself back to quadrant 2? And you would do that by adding 180 degrees to your calculator answer. So just a note that you want to adjust your answer to the quadrant where your complex number lies. And in that same vein of thinking, if your number was in quadrant 3 and your calculator gave you a quadrant 1 answer, again, you would need to add 180 degrees because your calculator is going to give you an answer up here, and your points down here, you would have to add 180 to get the correct coordinates or the correct angle for the terminal point of your complex number. So here, if we want to find the modulus or the absolute value, and you have the complex number -512, so you've moved over -5 and up 12. So this length is 5 in the negative direction, and this length is 12 in the positive direction. And the terminal point is up here at -512. Your hypotenuse is 13. So that finding the modulus or the absolute value is the square root of -5 squared plus 12 squared. And that's going to look like, what, 25 and 144. So square root of 169 is how we have that length is magnitude is 13, or modulus. And then secondly, if we want to find the angle theta, so we're going here, our theta is tan inverse of B over A. And we need our calculator to do the heavy thinking for us. So let's see, we need PI. So using our calculator, the inverse tangent of 12 over -5 is -1.17 radians. And we want to convert that by multiplying 180 and dividing by pi. So we have a -67.38 degrees. Now here's that first case of that. So if our calculator gives us this answer here, this is our calculator answer, I'm going to call that theta prime, and it's -67.38 degrees. And I want to know where I am over here. I've got to add 180 degrees to that. So theta prime is -67.38, and we want to add 180 to that to put us back into the right quadrant, since our terminal point is over here in quadrant 2, and that's 112.62 degrees. So our theta is about 112.62 degrees, right? Because it's given us this angle here, which is the measure of that inside there, and we are up here at 112 degrees. So magnitude 13 and direction angle 112.62. So here's one for you to try. It's fairly simple. Just by inspection, you can look at it and know that the length is going to be 7. Since your graph is down here, 7 units. This is where you are. And your angle measurement would be -90. So your magnitude or your modulus or absolute value, whatever terminology you want to call it, that's 7. And your angle theta would be 270 degrees if you went for the positive rotation, or 3 pi over 2 if you were going to answer in a radian measurement. So that one was fairly simple. Next, let's talk about polar form of a complex number. Sometimes that's called trig form of a complex number. So we know that, let's draw a picture here. You've got some, I'm not very good at that straight line stuff. See if we can do that better. So we've got some ray coming out to this point here. That's our terminal point. And that's my radius. And if we drop a perpendicular back to the x-axis, that's our imaginary length. This is our real number length. This is our angle. And we know that's a right triangle. So we're calling r is the modulus, which also happens to be the absolute value, the magnitude. And theta we're calling the argument. So we know that cosine is adjacent to hypotenuse, and sine is opposite to hypotenuse. So if we solve for a, we can multiply both sides by r. A is r cosine theta, and b is r sine theta. So if we substitute the a and the b in for our complex number, then z is r cosine theta plus I times the b value, which is r sine theta. And if you wanted to, you could factor out the r and write that in a simpler, more compact form. R times cosine theta plus I sine theta. And this is what is known as polar form or trigonometric form of a complex number. We started with the complex plane. We gave some definitions using the a and b and the modulus and came up with a form using trigonometry. So let's give this a try. If we write a complex number as the square root of 3 and then I, that means we're going to go on the real axis, square root of 3, and up 1i. So this is 1. This is my imaginary part. I've got the modulus, which is my r, and that should be 2 since our endpoint is 3, 1, square radical 3, 1. So my a value is radical 3, b value is 1. This looks like a 30, 60, 90 triangle where my angle is 30 degrees. And we already know the hypotenuse or the modulus is 2. So you could verify that your modulus is correct by calculating the length of the hypotenuse, which is 3 plus 1, that's 4. Square root of 4 is 2. And verify that for our modulus. And then writing that in complex form, our formula was r times cosine theta plus I sine theta. So using that format, our complex number in polar form is 2 times cosine, and I'm using degrees here, 30 degrees. If you wanted, you could put pi over 6, and I sine 30 degrees. So polar form of a complex number, or trigonometric form. Here's another one to try. We've got the square root of 6 as our a, and negative square root of 2 is our b. So we want to go down negative square root of 2 and go to the right square root of 6 and calculate what our argument is and what our modulus would be in this right triangle for that endpoint there. So our r is radical 6 squared, so that's 6. plus negative radical 2 squared, that's 4, and 6 plus 4, or I'm sorry, this is 6 plus 2 is radical 8, or you could simplify that to be 2 square roots of 2. We'll make it that. And then our angle would be, what, a negative 30 degrees? Or if you wanted to, you could say that's 330 degrees, or 11 pi over 6. This time, just to be different, we'll use the radian measurement. So our final step is z equals the modulus, which is 2 radical 2, times cosine 11 pi over 6 plus I sine 11 pi over 6. So just trying to keep those angle measurements positive instead of giving a negative angle measurement. It's prettier. In example 7, we're going to change polar form to rectangular form. So this is just the same thing. We're just going to go backwards. So looking at it, we know we need the actual cosine value of 3 pi over 4. And that's in quadrant 3, so it's negative square root of 2 over 2. And then likewise, the sine of 3 pi over 4. Again, that's a 45-degree angle, so they have the same values. So converting that, we have z is 5, and we're multiplying negative square root of 2 over 2, plus, we got the I in there, I times negative square root of 2 over 2. And then to simplify that down, we have negative 5 square roots of 2 over 2. And then, oh wait, this isn't in quadrant. Hold on, got a negative mistake there. Sine of 3 pi over 4 is in quadrant 2, so sine's positive. Don't let me make that mistake. And 5 square roots of 2 over 2 times the I. I'm going to put the I at the end. So this is my rectangular form. And if you really wanted to have a decimal approximation, so you could graph that and have some kind of idea about how big that size of that number is. That's roughly about negative 3.54 and positive 3.54 I in rectangular if you wanted to graph it on a piece of graph paper. Here's one more to try. So this one they've given us the complex number in standard form. So we need cosine of 240, which is negative 1/2. And the sine of 240, this actually is in quadrant 3, is negative square root of 3 over 2. So this is a 60-degree angle down in quadrant 3. So z is 3 times negative 1/2 plus I times negative root 3 over 2. So our rectangular form is negative 1.5 minus 3 times root 3. Minus 3 times the square root of 3 over 2 with the I for the imaginary part. Real number part, imaginary part. So those are fairly simple. Here we're going to take a look at operations with complex numbers. So when you multiply or find a product of two complex numbers, say z1 times z2, you're going to multiply the moduli. So the moduli is r1 and r sub 2, and then you want to add the arguments. So in the first case, we have cosine of theta sub 1 plus theta sub 2. And then the I is next, and sine of theta sub 1 plus theta sub 2. So it's pretty straightforward. If you're multiplying two complex numbers, you multiply the moduli and you add the arguments. The arguments are the angles. The moduli are the r's. Okay? Same thing with quotients. Quotients is the same thing, just different. If you're dividing two complex numbers, you divide the moduli and you subtract the arguments. Cosine of theta sub 1 minus theta sub 2 plus I times the sine of theta sub 1 minus theta sub 2. And then, of course, your z sub 2 can't be 0 because you'd have division by 0. So you just have to be careful of that. Okay? So let's give those a try. We want to multiply z1 times z2. So we've got 2 times 3. Those are my two moduli. And then we want to add 36 degrees and 114 degrees. And then repeat that for I sine 36 degrees and 114 degrees. So our product's going to be 6 and then cosine of 150 plus I sine of 150. And then you want to convert the cosine of 150 is negative square root of 3 over 2. And the sine of 150 is a half. So distributing our 6, we have negative 3 square roots of 3 plus 3i. And this is my rectangular form. So we started out with polar form, multiplied them together, and ended up with rectangular form. If you want to make a note of that, this is our rectangular form. And then if you needed to, you could easily graph that, going this distance on the real axis and this distance on the imaginary. Example 10 is going to be a division question. So dividing the first complex number by the second complex number. We're going to divide 2 by 6, so we're going to get a third. And then we want to subtract 240 minus 32, which is going to be 208. So this is going to force us to use a calculator here. And I sine 240 minus 32. So we've got 1/3 cosine 208 degrees, and I times the sine of 208 degrees. So with our calculator, we got the cosine of 208. Clear that out. The cosine of 208 degrees. And we got a third of that, so divided by 3, that's negative 0.294. So this is negative 0.294. And sine 208 should also be negative. So same thing, got the sine of 208 degrees divided by 3, and it's negative 0.156. So negative 0.156 with an I. Gotta make that look like minus here. Okay, so complex form, division, our answer turns out to be rectangular form. So pretty easy. Now, DeMoivre's theorem gives us a way to raise a complex number to a power. And you can tell by looking at the rule here that if you have a complex number raised to a power, you're going to raise the modulus to the power and then multiply each of the arguments by the power, provided that the power is at least 1 or greater. So this is our last operation. And we want to raise this number to the 4th power. So raising z to the 4th power, we're going to raise the modulus to the 4th power and multiply 15 degrees times 4. And do the same thing for the sine 15 degrees times 4. So that's looking like 60 degrees. So 2 to the 4th is 16, and 15 times 4 is 60. And then the I sine of 60. So the cosine of 60 is 1/2, and the sine of 60 is radical 3 over 2. So we've raised this complex number to the 4th power, and that 16 times 1/2 is 8, and 8, I'm going to put the I in front of the square root, 8i square roots of 3 for what's called standard form. So we've got rectangular form or standard form in that A plus BI format. So the real part and the imaginary part gives us our z to the 4th power in this case. So a couple more for you to try. In this case, we don't know our r value, so we want to raise this complex number to the 4th power. So we've got to figure out if you go square root of 3 to the right and 1 unit in the imaginary part, then our modulus is 2. And that's a 1 square root of 3, 2 triangle, so our angle is a 30-degree angle, or pi over 6. So our complex number is 2 cosine pi over 6 plus I sine pi over 6. And we want to raise that to the 4th power. So z to the 4th power is 2 to the 4th, which is 16. And we're multiplying 4 times pi over 6. So that becomes 4 pi over 6, or 2 pi over 3. And cosine of 2 pi over 3 is negative 1/2. And then the same thing with the sine of 2 pi over 3 is going to give us the square root of 3 over 2. So getting our z to the 4th power is 16 divided by negative 2, so negative 8 for the real part, and 8i radical 3 for the imaginary part. So this is our standard form for raising that complex number to the 4th power using DeMoivre's theorem. We had to convert to polar form to know what to do, right? We needed the angle and we needed the modulus. And then here, this last one, it's the same thing, but again, you have to think about if you go 1 unit on real and 1 unit on imaginary, our angle here is a 45-degree angle, and your hypotenuse or your modulus is radical 2. So converting that complex number into polar form, we know it's r cosine of 45 degrees, or pi over 4. It's probably easier if we left it pi over 4. Sine of pi over 4. And the reason I think it's easier is because it's easier to multiply pi over 4 times 5 than it is to do that math in your head. So raising that complex number in polar form to the 5th power, this is what I'm talking about. Cosine of 5 times pi over 4 is 5 pi over 4. And somehow just radians are easier to work with. So radical 2 raised to the 5th power, you know, we've got 5 of those. 1, 2, 3, 4, 5. So 1, 2, 3, 4. So we got 4 on the outside. That's 4 radical 2. And cosine of 5 pi over 4 is negative root 2 over 2. And it's the same value for sine in that angle. So our complex number in standard form is going to be, this is going to get rid of that. That's 2. And we got another 2. So we got negative 4 here. And then negative 4i on the imaginary part. So standard form is negative 4 minus 4i. And then the last skill we need in this section is if you have a complex number that satisfies the equation z to the n equals w, we can say that z is a complex or nth root of w. We can use DeMoivre's theorem to find those distinct roots where w is r cosine theta plus I sine theta in polar form. So here's what that looks like. This is our formula here. And you can see that we're taking our angle argument and adding 2 pi k over n, and same thing on the sine, adding 2 pi k over n. So let's give this a try. So we want to find the complex cube roots of 8 cosine 120 plus I sine 120. So we said the rule was, let's write the rule here. Z sub 0 is going to be the cube root. Well, first let's write the rule. Z to the k. So we're going to find the cube roots. So that would be r to the n cosine theta plus 2 pi k over n plus I sine theta plus 2 pi k over n. So there's our roadmap for our rule to follow. So we're going to look for, first of all, the first root, which is our r is 8 and our n is 3. We're looking for the cube root, This is our n. So we've got cosine of 120, that's our theta, plus 2 times 2 pi, that's 360. And our k, we're getting, this is our k, we're getting the 0 root. So 360 times the 0 root. And we're dividing by 3. Plus I sine 120 plus 360 times the 0th root divided by 3. Ooh, that's some messy stuff. So our 0th root is the cube root of 8, that's 2. And 120 plus 0 divided by 3 is the cosine of 40 plus I sine of 40. Now I'm not going to go get a decimal answer. I'm just going to leave it. That's my first root. The second one, the we'll call that z sub 1, is the cube root of 8. And again, we're going to repeat this. Cosine of 120, but this time it's 360 times 1, because they're saying n equals where our k is. We're going to go, k is going to go from 0, 1, and 2. And then we'll have the cube roots, the first one, the second one, and the third one. And we're dividing that by 3. And then same thing, I sine of 120 plus 360 times 1 divided by 3. And then our second root, which we're calling z sub 1, is going to be 2. And cosine, so we got 360 and 120, so that's 480 divided by 3. Is that 160? And then I sine 160. So there's the second root. And then our final one, z sub 2, is going to be same thing, but we're substituting a 2 to get this third 0, or third cube root. Cosine of 120 plus 360 times 2 divided by 3 plus I sine 120 plus 360 times 2, should make that red, divided by 3. So our third and final cube root would be 2 cosine, so do a little math here, that's 720, 360 times 2 plus 120, that's 840, divided by 3, that's 280. So we got 2 times cosine 280 plus I sine 280. So those are our 3 cube roots of that complex number, 8 cosine 120 plus I sine 120. That's the end of our lesson. See you next time.